Every detail in this story comes from real scientific research and observation. 7 points of light hang in the winter sky. Only 6 are ever easily seen. A cluster of more than 1,000 stars, born together, still moving together, for now. In 250 million years, this exact pattern will not exist. A star has just ignited, then another, all from the same collapsing cloud of gas. Greeks said 7 sisters fled a hunter across this sky, forever, and were never caught. In Japan, these same stars gave their name to a car company's badge. In New Zealand, their return in the winter sky marks the start of a new year. In 2022, that moment became a national holiday. In ancient Mexico, priests once let every fire in an empire go dark and waited on these stars to tell them if the world would continue. Aboriginal Australian traditions, tens of thousands of years old, tell an almost identical story of sisters and a pursuit. A satellite named Gaia has mapped these stars to a precision finer than a hair's width, seen from a mile away. One of these stars burns twice as hot as the sun, and because of that, it is already dying. A pale blue haze wraps around part of the cluster, light scattering through a cloud of dust that strangely has nothing to do with the stars at all. This is a story about sisters who were never actually 7, a fire that was almost allowed to die, and a pattern of light that nearly every human civilization has looked up at and tried to name. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Everything described tonight is built on real astronomical research, real historical record, and current scientific understanding of how stars are born, live, and drift apart. Just relax and feel free to let this play as it carries into sleep. Now, let us begin. High in the winter sky of the northern hemisphere, and low above the horizon in the southern one, a small cluster of stars catches the eye, even from a city rooftop with heavy light pollution. It sits about 444 light-years from Earth, a distance so large that the light arriving tonight left those stars around the time medieval astronomers in Europe and the Islamic world were still cataloging the positions of stars by hand. The stars themselves are young by the standards of stellar lifetimes, only about 100 million years old, all born from the same collapsing pocket of gas and dust at roughly the same moment in time. For most of human history, no one alive understood any of this. What they understood was simpler. The pattern was there, nearly every clear night, in nearly the same place, and it seemed to mean something. Long before telescopes, before written astronomy, before anyone had a word for a light year, people across entirely disconnected parts of the world looked up at this same small cluster of stars and built stories around it, separated by oceans, unaware of each other's existence. Cultures on nearly every inhabited continent identified this same cluster, gave it a name, and folded it into their understanding of time itself. That alone is worth pausing on. Of the thousands of stars visible to the naked eye on a clear night, this particular, faint, tightly packed group became one of the most universally recognized objects in the sky. Start with Greece. In the oldest surviving version of the story, 7 sisters, daughters of the Titan Atlas and the sea nymph Pleiades, were being pursued across the earth by the hunter Orion. The chase went on for years, according to the myth, with Orion never catching them and never giving up. Eventually, the gods intervened, transforming the sisters into stars to end the pursuit forever. But it did not end. Orion was also placed in the sky, and to this day the constellation that carries his name rises after the Pleiades and appears to chase them across the winter heavens, night after night, exactly as the story describes. The names of those 7 sisters, Maia, Electra, Taygete, Alcyone, Selino, Sterope, and Merope, are still the names astronomers use for the 7 brightest stars in the cluster today. This is not a coincidence or a modern nod to old mythology. It reflects how continuously this cluster has been observed and named by the same cultural tradition, stretching from ancient Greek poets through Roman astronomy and into the star catalogs used by professional observatories in the present day. Few objects in the sky carry a naming history this unbroken. The Greek poet Hesiod, writing around the 8th century BCE in a farming manual called Works and Days, used the rising and setting of this exact cluster as a practical calendar. He instructed farmers to begin the harvest when the cluster rose before the sun in late spring, and to begin plowing when it set before the sun in autumn. He also warned sailors that the safe sailing season ended around the cluster's setting in early November, after which the seas were considered too dangerous to cross. None of this required a written calendar or a count of days. It required only a clear sky and knowledge of where and when to look. There is a strange detail embedded in the Greek myth that later astronomers would find oddly appropriate. Ancient texts, including the poet Aratus, writing around the 3rd century BCE, describe the cluster as containing 7 stars, but note that most observers could only make out 6 with the naked eye. Multiple explanations circulated in antiquity that one sister hid her face in grief or faded from view out of shame. Whatever the reasoning, the ancient observation itself was accurate. Under real dark skies, without any modern light pollution, most human eyes can resolve about 6 stars clearly, occasionally 7 or more with excellent eyesight, and the actual number of stars belonging to the cluster is far, far higher than either figure. Now travel east to Japan. In Japanese, the cluster is called Subaru, meaning to unite or to govern, and referring to the way the stars appear gathered together in one place. This name is not obscure poetry lost to history. It is the same word and the same 6-star symbol used today on the badge of the automobile company Subaru, founded in 1953 as a merger of 5 smaller manufacturing companies. The logo shows 6 stars, 1 large star representing the parent company, and 5 smaller stars representing the companies that join together beneath it. Millions of people around the world see a stylized image of this exact star cluster every day on the front of a car, almost certainly without knowing what it depicts or how old the name behind it actually is. References to Subaru appear in Japanese literature stretching back over 1,000 years, including in the 11th century work The Pillow Book, where the cluster is named directly among a short list of the most beautiful things a person can see in the night sky. The astronomical accuracy embedded in that old text is notable. Whoever wrote it had clearly spent real time watching the sky, closely enough to single out this one small, faint cluster among everything else visible on a clear night, and to judge it worth writing down. Farming communities across the Japanese islands also used Subaru as a seasonal marker, much like Hesiod had used the same stars on the other side of the world. Its position in the evening sky helps signal the timing for rice planting and harvest in different regions, passed down through generations of oral and written agricultural knowledge, long before mechanical calendars were in common use. Two civilizations, with no contact between them, had independently arrived at the same conclusion, that this faint cluster of stars was reliable enough to organize a year's worth of labor around. Now, south of the equator, to New Zealand. For Maori communities across Aotearoa, New Zealand, this same cluster is known as Matariki, and its reappearance in the pre-dawn sky in late June marks the beginning of the new year. After weeks of being too close to the sun to observe, the cluster performs what astronomers call a heliacal rising, its first visible reappearance low on the eastern horizon just before sunrise. Traditionally, this rising was tracked carefully because its timing, combined with the phase of the moon, determined exactly when the New Year celebrations would begin. The event was tied closely to the turning of the seasons in the southern hemisphere, arriving during the depth of winter, a time of reflection, remembrance of those who had died in the previous year, and planning for planting season ahead. Matariki nearly disappeared as a widely observed tradition through the 20th century, but has undergone a significant revival in recent decades. In 2022, the New Zealand government formally recognized Matariki as a national public holiday, making it the only holiday in the country's calendar tied directly to an astronomical event rather than a fixed date. Each year, the exact date shifts slightly, calculated using the actual heliacal rising of the cluster and the lunar calendar, connecting a modern nation's public holiday schedule to the same act of skywatching that has been practiced in that region for centuries. The exact number of stars recognized varies between different IWI, or tribal traditions, but many accounts describe 9 visible stars, each carrying its own name and its own area of significance, differing from the 7-sister framework used in Greek tradition. Tupuanuku is associated with food grown in the ground, and Tupuarangi with food from above, such as fruit and birds. Waiti and Waita govern fresh water and salt water respectively, while Waipunarangi is linked to rain and Urarangi to wind. Pohutakawa is the star connected to those who have died in the past year, and Hua'aitarangi is associated with hopes and aspirations for the year ahead. The relative brightness and clarity of each star, observed carefully during the winter rising, was traditionally read as a forecast for the conditions of the coming year in that specific area of life. Now, further back in time to central Mexico. Among the Aztec people, this cluster held a role tied to nothing less than the survival of the world itself. Central to Aztec cosmology was the belief that the universe had already been destroyed and recreated multiple times, and that the current age could end again if the proper rituals were not performed. Every 52 years, the point at which the Aztec solar calendar and a separate ritual calendar realigned, priests conducted a ceremony known as the New Fire Ceremony, or Toxiomalpilia. All fires across the empire were extinguished, temples went dark, households broke their pottery and waited. Priests climbed to a sacred mountain outside the capital city and watched the sky for the Pleiades cluster to reach its zenith, the highest point in the sky, at midnight. If the cluster continued its normal path overhead, it meant the sun would rise again and the world would continue for another 52 years. A new fire was kindled at that exact moment, using a fire drill on the chest of a sacrifice, and messengers carried the flame by torch to reignite hearths across the entire empire before dawn. The last such ceremony under Aztec rule took place in 1507, only 12 years before the arrival of Hernán Cortés, and the beginning of Spanish colonization, which ended the tradition before another 52-year cycle could complete. Much of what is known about this ceremony today comes from the Florentine Codex, a 16th century manuscript compiled by the Spanish missionary Bernardino de Sahagún, working directly with Nahua scholars and eyewitnesses shortly after the conquest. According to that account, the anxiety surrounding the ceremony was genuine and widespread. People reportedly climbed onto their rooftops on ceremony night, watching the same patch of sky as the priests, and pregnant women were said to wear masks made of magi leaves out of fear that the end of the world, should it come, would transform them into monsters. Historical records suggest earlier ceremonies were held in years corresponding to 1351, 1403, and 1455 on the modern calendar, showing a tradition maintained with precision across generations, entirely dependent on accurately tracking the position of this single cluster of stars. Go back further still to Mesopotamia. The oldest surviving written reference to this cluster comes from ancient Babylon in a compendium of astronomical knowledge known as Mu-el-Apin, compiled from older observational records and dated to around 1000 BCE, though likely reflecting practices centuries older still. In it, the cluster is simply called Mu-el-Apin, meaning stars or star cluster, treated as important enough to require no more elaborate a name, as though it were the star cluster above all others. Babylonian astronomers used its heliacal rising, its first visible appearance in the dawn sky after a period of invisibility, as one of several fixed markers for calibrating their lunisolar calendar, a calendar that had to periodically insert an extra month to keep pace with the actual solar year. This cluster's rising, tracked and recorded across generations of court astronomers on clay tablets, some of which still survive in museum collections today, helped a civilization more than 3,000 years ago keep its calendar synchronized with the physical seasons. Travel now to the deserts of pre-Islamic Arabia. In classical Arabic, the cluster is called Al-Thuraya, and it appears repeatedly across centuries of Arabic poetry, often used as a symbol of beauty, distance, or a cluster of jewels scattered across dark cloth. Bedouin communities used its rising and setting to mark the start and end of the rainy season, a detail with direct practical consequences for herding and travel across arid terrain. Early Islamic astronomers inherited and expanded this tradition. Scholars working in Baghdad and Cordoba during the height of the Islamic Golden Age, roughly the 9th through 13th centuries, cataloged Al-Thuraya's position with real precision, folding it into a broader body of star tables that later fed into European astronomy during the medieval period. Now, further east to ancient China. Chinese astronomers independently built an entire cosmological system around 28 lunar mansions, segments of sky the moon passes through over the course of a month, used for both practical timekeeping and astrological interpretation. This cluster was designated Mao, one of those 28 mansions, with records of its observations stretching back over 2,000 years in official court astronomical documents. Court astronomers were tasked with tracking Mao's position and brightness as part of a broader duty to report celestial omens to the emperor, since unusual behavior in the sky was traditionally interpreted as reflecting on the legitimacy or fortune of the ruling dynasty. This means some of the oldest continuous written observational records of this cluster anywhere in the world come from Chinese imperial archives rather than from Europe or the Mediterranean. Closer to the present, in English literature. Alfred Lord Tennyson, poet laureate of the United Kingdom for much of the mid-19th century, wrote of watching this exact cluster rise through evening haze in his 1842 poem, Locksley Hall, comparing its scattered light to fireflies caught in a silver braid. Tennyson was known for his careful attention to natural detail, and this particular image reflects real, accurate observation, describing precisely how the cluster's loosely scattered stars appear to shimmer and blur together when viewed low on the horizon through humid evening air. His description has remained one of the most quoted literary references to this cluster in the English language for well over a century. One stop closer to home for many listening tonight. In North America, Kiowa and Lakota oral traditions tell a story centered on a real, physical place, the striking rock formation in present-day Wyoming known today as Devil's Tower, and to many indigenous nations as Bear's Lodge. According to the story, 7 young sisters were being chased by a giant bear. Trapped, they climbed onto a low rock and prayed for help, and the rock began rising beneath them, growing taller and taller into the sky. The bear, desperate to reach them, clawed at the sides of the rising rock, leaving deep vertical grooves down its entire height. Those claw marks in the story are the same vertical columns that give Devil's Tower its distinctive fluted appearance today, a real geological feature formed roughly 50 million years ago by the slow cooling and cracking of volcanic rock, entirely unrelated to the legend, but visually striking enough to have inspired it. In the story, the rock rose so high that the sisters were carried straight into the night sky, where they became the stars of this same cluster. What follows is not part of any recorded telling, only an imagined moment, offered here purely as illustration, with no claim to represent the story as any storyteller actually passed it down. Picture, only as illustration, the instant just before the rock began to rise, 7 sisters pressed together on a slab of pale stone, the bear's breath audible somewhere close in the dark, no path left in any direction but straight up. One version imagines the youngest sister looking down at her own hands and finding them already too far from the ground to jump, the stone beneath her feet already lifting, slowly, then faster, carrying all 7 upward past treetops, past cloud, past whatever a person standing below might have still been able to see. This specific particular moment appears in no known written account and should not be mistaken for one. It exists here only as a brief speculative bridge between 2 documented details already established, the physical rock and the story eventually placing 7 sisters among these same stars. One more stop to the deserts and coastlines of Australia. Aboriginal Australian communities across dozens of distinct language groups also hold stories about this cluster, predating European contact by tens of thousands of years, based on some of the oldest continuously practiced oral traditions on Earth. Many of these traditions, independently developed across a vast continent, similarly describe a group of sisters being pursued by one or more men across the sky, closely paralleling the Greek myth, despite there being no possible historical contact between these cultures. Some researchers who study these oral traditions have proposed that certain details, including references to a star that has since dimmed, or a star count that shifts between 6 and 7, may preserve real observations of subtle changes in the cluster's stars, passed down accurately across an extraordinary length of time, though this remains an area of ongoing and still developing research, rather than settled fact. One tradition from the Wurundjeri and neighboring peoples of southeastern Australia tells of the Karat Gurk, 7 sisters who were said to hold the secret of fire, each carrying a burning ember on the end of her digging stick. According to the story, they refused to share fire with the rest of the world until a crow, through trickery, managed to steal a single burning coal and finally gave the gift of fire to humankind. The sisters were later placed in the sky, still carrying their glowing embers, forming this same cluster of stars. What makes this pattern worth sitting with is not any one myth on its own. It is the repetition. Sisters. Pursuit. A missing or hidden star. A marker of time, of seasons, of new beginnings. Cultures with no contact, no shared language, no shared writing system, independently looked up at the same faint cluster of stars and arrived at strikingly similar stories. Whatever this cluster actually is, physically out there in the dark, it clearly did something to the human imagination that very few other objects in the sky ever managed to do. None of these observers had a telescope. None of them knew what a star actually was, in physical terms, a ball of plasma generating energy through nuclear fusion, millions of kilometers across, burning at temperatures of thousands of degrees. They worked entirely from pattern, position, and timing, tracked across centuries by eye alone. It raises a fair question. Once actual instruments were pointed at this cluster, what did they find underneath all those layers of story? Astronomers classify this object as an open cluster, a group of stars that form together from the same cloud of gas and dust and remain loosely bound by their mutual gravity, at least for a while. This distinguishes it from a globular cluster, a much older, much denser, and far more tightly bound type of grouping that can hold hundreds of thousands of stars in a tight gravitational knot for billions of years. Open clusters are different. They are younger, looser, and, as later parts of this story will explore, temporary. The formation process began in a giant molecular cloud, a vast region of cold hydrogen gas and dust stretching many light years across, dense enough in places to collapse under its own gravity. Somewhere within a cloud like this, roughly 100 million years ago, a region became unstable and began to fold in on itself. As it collapsed, it fragmented into thousands of smaller clumps, each one a seed for an individual star. Friction and gravitational compression heated the core of each clump until nuclear fusion ignited, and one by one, the stars of this cluster switched on, essentially simultaneously on any cosmic timescale, all within the same small pocket of space. A useful comparison exists much closer to home, astronomically speaking. The Orion Nebula, visible as a faint smudge below the 3 stars of Orion's belt, is an active stellar nursery right now, producing new stars out of collapsing gas in exactly the same way this cluster's stars were produced roughly 100 million years ago. Looking at the Orion Nebula tonight is, in a real sense, looking at what this cluster would have looked like in its own infancy, wrapped in the glowing, turbulent gas of its birth cloud, before that gas was blown away by the very stars it had just created. That number, 100 million years, is not a rough guess. Astronomers determine stellar ages using a technique called isochrone fitting, which compares the brightness and color of every star in a cluster against detailed physical models of how stars of different masses evolve over time. Heavier, hotter stars burn through their nuclear fuel and change color and brightness far faster than smaller, cooler ones. By plotting every member star on a chart of brightness against temperature and finding which stellar evolution model best matches the resulting pattern, researchers can pin down the age of an entire cluster with real precision. For this particular cluster, That method consistently returns an age close to 100 million years, young enough that dinosaurs, extinct on Earth for tens of millions of years by that point, never saw a single one of these stars in the sky. The exact number of stars belonging to this cluster is far higher than the 6 or 7 visible to the naked eye. Modern surveys, especially recent data from the European Space Agency's Gaia satellite, have identified more than 1,000 confirmed member stars, tracked and verified because they share a common motion through space, drifting together in the same direction at nearly the same speed, a gravitational family fingerprint that cannot be faked or confused with unrelated background stars. Most of these 1,000+ stars are small, dim, reddish stars, far below naked eye visibility, vastly outnumbering the handful of bright, hot, blue-white stars that make the cluster recognizable from a backyard on a clear night. Visibility itself depends heavily on conditions. Under genuinely dark skies, away from artificial light, most people with normal eyesight can pick out 6 stars without difficulty, and observers with sharper vision, or simply more patience, can often resolve 8, 9, or occasionally more. Under the light-polluted skies most people live beneath today, 3 or 4 is more typical, and in a heavily lit city, the cluster can vanish from naked eye view entirely, reduced to a faint, unresolved smudge, or nothing at all. A basic pair of binoculars changes the experience entirely. Even inexpensive ones, held steady, resolve dozens of individual stars where the naked eye saw only a handful, revealing the loose, scattered structure of the cluster far more clearly than a small telescope actually can. This happens because the cluster spans roughly 2 full degrees of sky, about 4 times the apparent width of a full moon, wider than the field of view most telescopes are built to show in a single frame. Wide, low magnification optics, ironically, reveal more of this particular object than powerful ones do. There is one more detail hiding in the space around these stars. The German astronomer Wilhelm Tempel first noticed something the naked eye and casual observation had always missed while observing this cluster through a small 4-inch refractor from Venice in October of 1859. Faint, wispy trails of pale blue light wrapped around several of the brightest stars, most noticeably around the star Merope. Tempel had sketched the cluster months earlier, and comparing that sketch against the sky again, he noticed a subtle haze that had not been there before, or that he simply had not previously registered. His report of the finding was met with skepticism for years afterward, since several other astronomers, observing with even larger telescopes, initially failed to see the same faint glow at all. This turned out to be a reflection nebula, a cloud of interstellar dust illuminated not by its own light, but by starlight scattering off its microscopic particles, the same physical principle applied on a cosmic scale that scatters blue wavelengths preferentially in Earth's own daytime sky. The physics behind that blue color comes down to the size of the dust grains involved. Interstellar dust particles in this cloud are typically smaller than the wavelength of visible light, and particles that small scatter shorter, bluer wavelengths far more efficiently than longer, redder ones. For exactly the same reason Earth's atmosphere scatters blue sunlight into every direction and produces a blue daytime sky. Photograph the nebula through a long exposure, gathering far more light than any human eye can process in real time, and that faint, cool blue glow becomes clearly visible, wrapped delicately around the brightest stars like smoke caught in a beam of light. For a long time, astronomers assumed this dust was left over from the cluster's own formation, remnants of the birth cloud still clinging to its newborn stars. Later, more precise measurements of the dust cloud's motion through space told a different story. The dust is moving through the same region of space at a different velocity than the stars themselves, meaning the cluster is not wrapped in its own leftover birth material at all. It is, essentially by coincidence, currently passing through and lighting up an entirely unrelated cloud of interstellar dust that happens to occupy the same patch of sky at this particular moment in cosmic time, a chance encounter rather than a lingering birthmark. Now, the question of distance. For most of human history, there was no way to know how far away any star actually was, let alone this specific cluster. The breakthrough came from a technique called trigonometric parallax, which uses the diameter of Earth's own orbit around the Sun as a measuring baseline. By observing a nearby star's position against the background of much more distant stars in, say, January, and then again in July, when Earth has moved to the opposite side of its orbit, astronomers can measure a tiny apparent shift in that star's position. Basic trigonometry, using the known width of Earth's orbit as one side of a very long, very thin triangle, then converts that shift into an actual distance. Before any satellite existed, 19th and 20th century astronomers relied on a related technique called the moving cluster method. Because every star in this cluster travels through space together, sharing the same direction and speed, their individual paths across the sky, tracked patiently over decades of photographic plates, appear to converge toward a single distant point, much like the parallel rails of a railway track appear to meet at the horizon. The angle of that apparent convergence, combined with each star's measured velocity toward or away from Earth, could be used to calculate distance without needing any space-based instrument at all, a clever workaround that produced distance estimates decades before Hipparcos ever launched. This cluster physically spans roughly 8 light-years across its densest core, though its full extended halo of gravitationally associated stars reaches considerably wider, and its combined mass, adding up every one of its 1,000+ members, comes to somewhere around 800 times the mass of the Sun. That may sound enormous, but spread across a region 8 light-years wide, the actual density of stars remains low by cosmic standards, with enormous gaps of empty space separating individual stars, even at the cluster's crowded core, nothing like the tightly packed imagery a word like cluster might suggest. Parallax works well for relatively nearby stars, but the angles involved shrink rapidly with distance, becoming difficult to measure accurately from the ground. The European Space Agency's Hipparcos satellite, operating between 1989 and 1993, was the first spacecraft designed specifically to measure these tiny shifts from the stability of space, free from the blurring effects of Earth's atmosphere. When Hipparcos returned its measurement for this cluster, the result was unexpectedly controversial. A distance of about 390 light-years, noticeably closer than the roughly 440 light-years produced by other, independent methods, including comparing the cluster's stars to well-calibrated stars of known distance elsewhere in the galaxy. That discrepancy mattered more than it might sound. Distances to nearby star clusters like this one form part of what astronomers call the cosmic distance ladder, a chain of overlapping measurement techniques used to calibrate distances to objects far too distant for parallax to work at all, ultimately underpinning distance estimates for galaxies billions of light-years away. A cluster this close, this well-studied, and this fundamental to calibrating other methods was not supposed to produce two seriously conflicting answers. For over a decade, The disagreement, sometimes called the Pleiades distance controversy, remained an open, mildly embarrassing problem in observational astronomy. The resolution came from Gaia, the European Space Agency's successor mission to Hipparchus, launched in 2013 and designed to measure the positions of over 1 billion stars with a precision roughly 100 times finer than its predecessor. Gaia operates from a stable orbital position about 1.5 million kilometers from Earth, slowly rotating and scanning strips of the entire sky over and over across its operational lifetime, building up millions of independent position measurements for every star it observes. Combining that many repeated measurements over years of operation is what allows its parallax calculations to reach a level of precision comparable to measuring the width of a human hair from a distance of over 1,000 kilometers away, a level of accuracy that would have sounded like fiction to the astronomers who first attempted parallax measurements by hand in the 19th century. Gaia's data releases through the following decade converged on a distance of approximately 444 light-years, matching the older independent methods almost exactly, and revealing that the original Hipparchus measurement had likely been affected by subtle systematic errors related to the satellite scanning method and the cluster's own internal motion. The controversy, once a genuine puzzle, is now considered closed, and this cluster stands as one of the more precisely measured objects in the night sky, its distance now known to within a small fraction of a percent. Gaia's data revealed something else, almost as a side effect of measuring distance so precisely. The cluster is not sitting still. It is moving through the Milky Way at roughly 40 kilometers per second relative to the Sun, carrying its more than 1,000 member stars along together in loose formation on a slow million-year journey through the wider structure of the galaxy. That shared motion is, in fact, the very thing that lets astronomers confirm which stars truly belong to the cluster in the first place, distinguishing true members from unrelated stars that simply happen to lie along the same line of sight. This cluster has also quietly rewritten a chapter of astrophysics itself. In 1995, a team of Spanish astronomers working at the Tate Observatory in the Canary Islands identified a faint, cool object within this cluster that did not fit any known category of star. It was too massive to be a planet, but too small and too cool to sustain the same hydrogen fusion process that powers ordinary stars like the Sun. The object, later named Theta 1, became the first confirmed brown dwarf in the history of astronomy, a long theorized but never verified type of object, sometimes described as a failed star. Brown dwarfs occupy a strange middle category, massive enough to briefly fuse a rarer form of hydrogen called deuterium early in their existence, but never massive enough to sustain the fusion of ordinary hydrogen the way true stars do. This cluster's well-established age and distance made it an ideal testing ground for confirming the theoretical properties of such an object, since its faint brightness could be directly compared against models predicting exactly how a 100-million-year-old failed star should look. Since that first discovery, dozens of additional brown dwarfs and extremely low-mass stars have been identified among this cluster's fainter, previously overlooked members, each one adding further detail to the picture of exactly how small an object can be and still technically ignite. Spectroscopy adds one more layer to this picture. Passing starlight through a prism-like instrument called a spectrograph splits it into a detailed rainbow crossed with thousands of thin dark lines, each one corresponding to a specific chemical element absorbing light at a precise wavelength. Applied to this cluster's stars, That technique reveals a chemical composition strikingly similar to the Sun's, roughly 70% hydrogen, a quarter helium, and a small remaining fraction of heavier elements, including carbon, oxygen, and iron, all forged inside earlier generations of stars that lived, fused heavier elements, and exploded long before this cluster ever formed. That detail matters more than it first appears. Every atom of iron in a listener's own bloodstream, every atom of oxygen in the air filling a room right now, was manufactured inside the core of some earlier star, one that finished its life and scattered its material back into the galaxy well before the Sun, the Earth, or this particular cluster ever existed. The stars overhead tonight are, in a very literal chemical sense, built from the recycled remains of stars that came before them, and so is everything else made of matter heavier than hydrogen and helium. Confirming exactly which stars belong to this family takes more than tracking their motion alone. Astronomers cross-check candidate members using a tool called a color magnitude diagram, plotting each star's true brightness against its color, which correlates directly with surface temperature, because every star in a genuine cluster formed at the same time from the same material. They trace out a distinctive, recognizable curve on that diagram, and any star that falls noticeably off that curve is very likely an unrelated foreground or background object caught by coincidence along the same line of sight. A second confirmation comes from something less visible: X-ray light. Young stars, still settling into a stable, mature phase of nuclear fusion, tend to have more turbulent, magnetically active outer layers than older stars like the Sun, producing significantly more X-ray emission as a natural side effect. Space telescopes sensitive to X-rays have used this elevated activity as an independent fingerprint of youth, helping confirm faint, low-mass candidate members that might otherwise be difficult to distinguish from older, unrelated stars using visible light alone. One question naturally follows from all of this: are there planets out there? Searching for planets around this cluster's stars has proven genuinely difficult, precisely because the stars are so young and, in many cases, so magnetically active. The two most common planet hunting techniques, watching for a slight dimming as a planet crosses in front of its star, or watching for a slight wobble in the star's motion caused by a planet's gravity, both struggle against the noisy, flickering light output of young, active stars, which can easily mimic or mask the signals astronomers are searching for. Despite that difficulty, a small number of candidate planets and planet-forming disks have been identified around individual members in recent years, and ongoing observation continues, treating this cluster as a rare nearby laboratory for catching planetary systems in the earliest, messiest stages of their own formation. Even the handful of bright points visible to the naked eye are hiding something. Several of the named stars that gave this cluster its mythological identity are not single stars at all, but tightly bound pairs or small groups of stars orbiting a shared center of mass, too close together to separate visually without a telescope. Atlas and Pleiades, representing the parents in the Greek myth, sit close together in the sky and are themselves each part of their own multiple star systems, while Alcyone, generally recognized as the cluster's single brightest point of light, is now known to be at least a double star, its fainter companion discovered only through careful spectroscopic analysis rather than direct sight. What ancient observers described as 7 or 9 individual points of light was, in physical reality, a somewhat larger and considerably more tangled family than any single myth accounted for. Behind every one of the stories told earlier in this account, the fleeing sisters, the badge on a car, the new year rising, the fire that was allowed to almost die, sits this same physical reality, a group of young, hot stars, born together roughly 100 million years ago, currently drifting through an unrelated cloud of dust, 444 light years from where this is being told. The next part of this account moves closer still, toward the individual stars themselves, each one with its own mass, its own temperature, and its own considerably shorter future. A star, up close, is never really a single point of light. It is a specific mass, a specific temperature, a specific rate of spin, a specific chemical mixture, and a specific position on a timeline that runs from birth to eventual death, all compressed into a pinprick the naked eye cannot begin to resolve. The 8 names inherited from Greek mythology, Atlas, Pleione, and their 7 daughters, now correspond to 8 specific entries in modern stellar catalogs, each one measured, classified, and in several cases found to be stranger than the myth ever suggested. Begin with the brightest. Alcyone, formerly catalogued as Eta Tauri, is the brightest star in the cluster and often treated as its central figure, much as it was in ancient tradition. It is a blue-white giant roughly 6 times the mass of the Sun, with a surface temperature close to 13,000 degrees Celsius, more than twice as hot as the Sun's own surface, and a luminosity around 1,000 times greater. None of that brightness comes from size alone. A star this massive burns through its nuclear fuel far faster than a smaller star does, trading a short, brilliant life for the Sun's comparatively slow, steady one. Alcyone is not alone, in the most literal sense. Careful spectroscopic analysis, splitting its light into detailed patterns rather than simply measuring its brightness, revealed a fainter companion star orbiting closely enough that no telescope has ever separated the two visually. What looks like one point of light from Earth is in physical reality at least 2 stars locked in a shared orbit, invisible to direct sight, but unmistakable in the data. Alcyone's apparent brightness, as measured from Earth, comes to roughly magnitude 2.9 on the scale astronomers use to rank how bright an object appears in the sky, a scale where lower numbers mean brighter and where the faintest objects visible to an unaided eye under good dark sky conditions sit around magnitude 6. In 1846, the German astronomer Johann Heinrich von Mädler, working at the Dorpat Observatory, proposed something considerably bolder about this star than its brightness alone, that Alcyone might sit at the physical center of a vast stellar system with the Sun itself and every other visible star slowly orbiting around it over an immense span of time. Mädler based this idea on his failure to detect any measurable proper motion among the cluster's brightest stars relative to one another, which he interpreted as evidence of a fixed central anchor point. Other astronomers of the period, including the Russian-German astronomer Friedrich Georg Wilhelm Struve, quickly challenged the idea, and improved measurements over the following decades showed no such central structure existed, leaving Mädler's theory as an interesting historical detour rather than a lasting discovery, though it briefly made this single-named star, for a few years in the middle of the 19th century, a candidate for the literal center of the known universe. That places Alcyone comfortably within easy naked eye range, despite sitting over 400 light-years away, a testament to just how much intrinsic light output a star 1,000 times more luminous than the Sun actually produces across that enormous distance. Even at that brightness, directly measuring a star's actual physical diameter from Earth remains extraordinarily difficult, since every star in this cluster appears, through even the largest ground-based telescopes, as nothing more than an unresolved point of light rather than a visible disk. Modern optical interferometry solves this by combining light collected simultaneously from multiple separate telescopes, sometimes kilometers apart, and using the resulting interference pattern to reconstruct details far smaller than any single telescope could resolve on its own. Applied to a handful of this cluster's brighter members, the technique has confirmed physical diameters several times larger than the Sun, consistent with what mass and temperature measurements alone had already predicted. Now, the parents of the myth. Atlas, the star representing the Titan of the same name, sits at one edge of the visible cluster and is itself a multiple star system, its light coming from at least two, and possibly more, closely orbiting companions. Pleiades, representing his wife in the myth, orbits nearby and turns out to be one of the more genuinely unusual stars in the entire cluster, a category of object astronomers call a shell star. A shell star is a rapidly rotating star, spinning so close to the physical limit at which its own gravity can no longer hold its outer layers together that it periodically flings material outward from its equator, forming a thin glowing disk of gas around itself. Pleiades' rotation has been measured at speeds approaching the threshold where the star would begin tearing itself apart, and its brightness genuinely fluctuates over months and years as that surrounding disk of ejected material forms, thickens, and gradually disperses back into space. Ancient observers who described one of the seven sisters as fading from view, hiding her face, or disappearing from the sky may, without knowing anything about stellar physics, have been describing something real. Pleiades' brightness does shift enough over long enough timescales to plausibly affect how many stars a naked eye observer could count in a given decade. This is not only ancient speculation. Modern astronomers have directly documented Pleiades moving in and out of active shell star episodes across the past century, with recorded changes in brightness and in the spectral signature of its surrounding disk occurring in the 1930s, again around 1972, and once more beginning in 2019, each episode lasting years before the star settled back into a quieter state. During the most active phases, the star's light passes through enough surrounding ejected gas to measurably dim and redden it, a real, tracked, physical event unfolding on a single-named star within this cluster across the lifetime of anyone listening tonight who happens to be old enough to remember the 1970s. Pleiades is not the only member of this cluster to display this kind of behavior. Astronomers classify stars that periodically eject material into a surrounding disk this way as B stars, a specific subcategory of hot, rapidly rotating Class B stars marked by distinctive emission lines in their spectra, bright spikes rather than the usual dark absorption lines, produced by glowing gas in the surrounding disk rather than the star's own surface. Merope and, at times, Atlas have also shown emission line behavior consistent with this same category, suggesting that the rapid, near-breakup rotation responsible for Pleiades episodes may be a shared trait among several of this cluster's brightest members, rather than an isolated oddity confined to just one star. The remaining daughters, each distinct. Maya, third brightest in the cluster, is a blue giant whose name was borrowed by the ancient Romans for the month of May, itself associated with the goddess Maya, and, by extension, with this star's seasonal visibility in the ancient calendar. Electra, nearly as bright, is another blue-white giant, similar in temperature and mass to Maya, though slightly less massive, and shows no unusual behavior beyond the ordinary brilliance expected of a young hot star, still early in its main sequence life. Taygeta is smaller than the brightest members, but turns out, on closer inspection, to be a spectroscopic binary as well, two stars orbiting closely enough to blur into a single point of light from any distance. Pleiades and Sterope, the two faintest of the traditionally named seven, sit right at the edge of naked eye visibility under good conditions, which may explain why ancient skywatchers across multiple unconnected cultures so often described the group as containing a star that was difficult or impossible to see. Sterope itself was later found to be not one star but two, now distinguished in modern catalogs as Sterope Porn and Sterope 2, sitting close enough together in the sky that ancient observers had no way of knowing they were looking at a pair rather than a single point. Measured precisely, the brightness of these fainter named stars sits close to the practical limit of unaided human vision. Pleiades registers at approximately magnitude 5.4, and Sterope at close to magnitude 5.6, both nudging up against the roughly magnitude 6 threshold below which the human eye, even under excellent dark sky conditions, simply stops resolving a point of light as a distinct star at all. Merope, brighter than either at around magnitude 4.2, remains comfortably visible under most reasonably dark skies, though its light is measurably softened by the same reflection nebula dust already described, scattering and slightly dimming its light on the way to any observer's eye. There is a way to measure how fast a star is spinning without ever seeing it spin. Astronomers determine a star's rotation speed by studying how its absorption lines, the same dark bands used to identify chemical elements, spread and blur in its spectrum. One edge of a rotating star is always turning toward Earth, while the opposite edge turns away, and that motion shifts the light from each side very slightly in opposite directions through the Doppler effect, smearing out lines that would otherwise appear as sharp, narrow bands. Applied to this cluster's brightest members, the technique reveals that several, including Pleiades and Alcyone, rotate remarkably quickly, in some cases completing a full rotation in under a day, compared to the Sun's own leisurely rotation period of roughly 27 days. That rapid spin is not incidental to these stars' behavior. A star spinning close to its physical breakup speed experiences reduced effective gravity at its equator, making it easier for stellar winds and radiation pressure to lift material away from the surface entirely, which is precisely the mechanism believed to drive Pleiades' recurring shell episodes. Slower spinning stars, including most stars closer in mass to the Sun, rarely display this kind of dramatic, self-generated mass loss at all. That same intense heat radiates far beyond the narrow band of light human eyes can detect. A surface temperature above 10,000 degrees Celsius pushes the bulk of a star's total energy output well into the ultraviolet range of the electromagnetic spectrum, largely invisible without specialized instruments, meaning the true energy output of this cluster's brightest members is considerably higher than even their impressive visible brightness alone suggests. That excess ultraviolet radiation is intense enough to measurably ionize nearby interstellar gas, stripping electrons from surrounding atoms across a modest surrounding volume of space, a subtle glow detectable to radio and ultraviolet telescopes, even where no visible nebula is apparent to the eye. All of this belongs to one particular category of star. Every one of these named, bright blue-white members belongs to spectral class B, a classification based on surface temperature and the specific pattern of dark absorption lines visible in a star's light when passed through a spectrograph. Class B stars sit near the hot end of the full stellar classification sequence, hotter and more massive than the Sun, but short of the rarer, even hotter Class O stars found at the extreme edge of stellar possibility. This particular blend of heat, mass, and color is precisely what gives the cluster its distinctive icy blue-white sparkle when viewed through binoculars, entirely different from the warmer yellow-white light of a sun-like star. The full classification system, running from hottest to coolest, uses the sequence O, B, A, F, G, K, and M, a set of letters that no longer follows any logical alphabetical order because the system was reorganized by temperature only after it had already been assigned decades earlier based on the strength of hydrogen absorption lines alone. The Sun sits comfortably in the middle of this sequence, a Class G star with a surface temperature around 5,700 degrees Celsius, distinctly cooler, yellower, and, on any human timescale, considerably longer lived than anything currently visible among this cluster's named members. Every one of the bright mythologized stars overhead tonight belongs to a hotter, rarer, shorter-lived category than the star providing daylight to whoever eventually watches a sunrise after this recording ends. That heat and mass come at a direct cost, measured in time, a star's total lifespan on the hydrogen-fusing portion of its existence, the stable, long middle stretch astronomers call the main sequence, depends heavily on its mass, and the relationship is not gentle. A star several times more massive than the Sun does not last several times longer. It burns through its supply of nuclear fuel dramatically faster, in some cases living for only a few tens of millions of years before exhausting the hydrogen at its core, compared to the Sun's roughly 10 billion year total main sequence lifetime. Part of that difference comes down to which nuclear process actually powers the star. The Sun generates most of its energy through a relatively gentle chain reaction called the proton-proton chain, fusing hydrogen nuclei together in a sequence of steps. Stars as hot and massive as this cluster's brightest members instead rely primarily on a faster, more efficient process called the CNO cycle, which uses carbon, nitrogen, and oxygen nuclei already present in the star as a kind of catalyst to fuse hydrogen at a dramatically higher rate, a direct consequence of the much higher core temperatures a massive star's stronger gravity produces. This puts the cluster's age in a new light. At roughly 100 million years old, this cluster is young by the standards of the universe, younger than most stars visible in the night sky, younger than the vast majority of stars in the galaxy as a whole. But for its own brightest, most massive members, 100 million years is not a small fraction of a long life. It may already represent a substantial portion of the total time those particular stars have left before their nuclear fuel runs low and their structure begins to change dramatically. This is not a distant, abstract concern reserved for some far future. The most massive stars in this cluster are, on stellar timescales, already well into what amounts to their own middle age, and within the next several tens of millions of years, several of them are expected to begin exhausting the hydrogen at their cores, swelling into cooler, larger red giants as their internal structure shifts to burning heavier elements in expanding outer shells. What happens after that depends heavily on each star's exact mass. Stars toward the lower end of this cluster's massive members will likely shed their outer layers gently, exposing a dense, slowly cooling core known as a white dwarf, roughly the size of Earth, but packed with the mass of a star. the heaviest members raise a more dramatic possibility. Whether any individual star in this cluster is massive enough to end its life as a supernova, a catastrophic explosive collapse rather than a gentle shedding of outer layers, depends on crossing a mass threshold estimated at around 8 to 10 times the mass of the Sun, a boundary that current measurements place this cluster's most massive members close to, without settling the question definitively in either direction. If any do cross that threshold before evolving off the main sequence, the eventual result would be a genuine core collapse supernova, one of the most energetic events physics allows, briefly outshining an entire galaxy before fading into a dense neutron star, or, in the most extreme cases, a black hole. The dividing line between these two very different endings, a gentle white dwarf or a violent supernova, ultimately traces back to a specific physical limit called the Chandrasekhar limit, a boundary of roughly 1.4 times the mass of the Sun, named for the astrophysicist Subrahmanyan Chandrasekhar, who first calculated it mathematically in the 1930s. Below that limit, the collapsing core of a dying star can be held stable indefinitely by a quantum mechanical effect called electron degeneracy pressure, essentially electrons refusing to be squeezed any closer together, producing a stable white dwarf. Above it, that same quantum pressure fails, and the core collapses catastrophically in a fraction of a second, triggering the explosive rebound that powers a supernova. That is not a prediction for tonight, or for any night soon. Even the fastest evolving stars in this cluster have tens of millions of years of stable burning left ahead of them, but it marks a genuine, physically grounded fork in this story's future, one written directly into the measured mass of specific, individually named points of light still visible, tonight, exactly where ancient skywatchers first placed them in their oldest stories. Not every member of this family shares that dramatic future. For every bright blue-white giant carrying a name from Greek mythology, this cluster contains hundreds of far fainter, far smaller stars, cooler and dimmer than the Sun, invisible without a telescope, and entirely absent from any ancient myth. These lower mass members will do almost the opposite of their brighter siblings. Rather than racing through a short, brilliant life, they will burn slowly and steadily for tens of billions of years, far longer than the current age of the universe itself, quietly outlasting every bright, mythologized star that made this cluster famous in the first place. That contrast between a handful of brilliant, short-lived giants and a much larger, quieter population of small, patient stars is not unique to this cluster. It reflects a basic pattern found in essentially every star-forming region across the galaxy. A small number of hot, massive stars capture nearly all of the visible attention and nearly all of the mythology, while the overwhelming majority of any cluster's actual stellar population consists of smaller, dimmer stars that no ancient observer working only with the naked eye would ever have known existed at all. One last pattern connects nearly everything already described. Statistically, across the galaxy as a whole, massive stars similar to this cluster's brightest members are more likely than not to have at least one close companion, a tendency confirmed repeatedly among Alcyone, Atlas, Tegeta, and Sterope, each already identified as multiple systems rather than single stars. Astronomers still debate exactly why massive star formation so often produces close pairs rather than solitary stars, with leading explanations involving the way a large collapsing gas cloud tends to fragment unevenly, or the gravitational pull of a forming star's own surrounding disk, splitting material into two separate cores rather than one. Whatever the precise mechanism, This cluster, small as it looks from Earth, currently serves as one of the more convenient and well-studied real-world test cases for working out exactly how that process unfolds. Every star described so far, from Alcyone's hidden companion to Pleione's shedding disk, to the quiet, uncounted hundreds with no name at all, shares one thing in common. None of them will remain exactly where they are now. Individual stellar lives, ending in white dwarfs or supernovae over tens of millions of years, are only one layer of change already written into this cluster's future. A second, slower, and in some ways more certain force is already at work as well, one that has nothing to do with any single star's internal fusion, and everything to do with the pull of the wider galaxy these stars are all embedded within. A cluster of stars does not stay bound together by accident, and it does not stay bound together forever. Gravity holds this group in loose formation for now, each star's motion balanced against the combined pull of every other star nearby. But that balance is neither perfect nor permanent. The same galaxy that gave this cluster its stars and its stage is also, slowly and steadily, working to take it apart. Begin with the invisible hand doing the pulling. Every star in this cluster orbits the center of the Milky Way galaxy, roughly 26,000 light-years away, completing one full galactic orbit in something on the order of 200 million years. That orbit does not proceed through empty, undisturbed space. The cluster periodically passes near other massive objects, other star clusters, dense clouds of interstellar gas, and, over its full orbit, occasionally sweeps closer to the crowded, gravitationally busy central regions of the galaxy itself, each encounter exerting a small gravitational tug on the cluster's structure. Two kinds of encounter matter most: the Milky Way's spiral arms, the bright star-forming bands that give the galaxy its familiar pinwheel appearance, are regions of noticeably higher stellar and gas density than the quieter space between them, and a cluster passing through one experiences measurably stronger and more frequent gravitational disturbances than it does while crossing the emptier gaps in between. Even more disruptive on occasion is a close pass near a genuinely massive giant molecular cloud, a concentrated region of gas and dust, potentially containing hundreds of thousands of times the sun's mass in a relatively compact volume, capable of delivering a single strong gravitational jolt sufficient to strip away a meaningful number of loosely bound outer members in one encounter, rather than through gradual, steady erosion alone. Astronomers call this general effect tidal stripping, borrowing the same basic physics that produces ocean tides on Earth, where the moon pulls slightly harder on the near side of the planet than the far side, stretching the water into a bulge. Applied to a star cluster instead of an ocean, the galaxy's gravity pulls slightly harder on the side of the cluster nearer the galactic center than the side farther away, creating a gentle, persistent stretching force that very gradually works individual stars loose from the group, particularly those already sitting near the outer edge of the cluster's gravitational reach. Open clusters like this one stand in sharp contrast to a different, far more durable category of star grouping: globular clusters, dense, roughly spherical swarms that can each contain hundreds of thousands of stars, bound together tightly enough by their own sheer mass to survive largely intact for over 10 billion years, older than most individual stars in the galaxy's outer regions. The difference comes down almost entirely to gravitational self-binding. A globular cluster's much greater total mass and density allow it to resist the same tidal stretching and internal evaporation processes that will fully dissolve a comparatively loose, lightweight open cluster like this one within a few 100 million years, rather than several billion. That outer edge is not arbitrary. Astronomers define a specific boundary called the tidal radius, sometimes referred to as the Jacobi radius, marking the maximum distance from a cluster's center at which its own gravity can still hold on to a star more strongly than the wider galaxy's gravity pulls that same star away. Stars orbiting comfortably within this radius remain gravitationally bound to the cluster, at least for now, while stars that drift or are nudged beyond it are effectively released, free to follow their own independent path through the galaxy from that point onward. For this cluster, current estimates place that boundary at somewhere around 43 light-years from its center, a radius the newly discovered tidal stream already extends far beyond. There is also a second, quieter mechanism at work, entirely internal to the cluster itself. Stars within the cluster do not move in perfectly parallel lines. They drift, wander, and occasionally pass close to one another, and each close encounter exchanges a small amount of orbital energy between the two stars involved, exactly as a gravitational slingshot exchanges energy between a spacecraft and a planet it passes near. Over many such encounters, spread across millions of years, lower mass stars tend to lose orbital energy on average and sink toward the cluster's gravitational center, while higher mass stars tend to gain energy and drift outward, eventually gaining enough speed to escape the cluster's gravity entirely. Occasionally, this process produces something more dramatic than a gentle drift. Astronomers use the term runaway star for a star ejected from its birth cluster at unusually high speed, sometimes tens of kilometers per second faster than its former neighbors, typically the result of an especially close gravitational encounter between 2 or 3 stars that flings one of them outward with far more force than the slow, average process of dynamical evaporation alone would produce. Several known runaway stars elsewhere in the galaxy have been traced back, through careful reconstruction of their past trajectories, to specific birth clusters they no longer visibly resemble or belong to, offering direct individual confirmation of the same ejection process currently unfolding, more gradually, across this particular cluster. This process, called dynamical evaporation, means the cluster is not simply drifting apart uniformly, with every star gradually spreading out at the same steady rate. It is actively sorting itself, ejecting individual stars one at a time, more often flinging away lower mass members than one might expect, in a slow, ongoing process that has almost certainly already carried away a meaningful fraction of this cluster's original stellar population, unnoticed and untracked across the roughly 100 million years since its formation. That process is no longer only theoretical, it has been directly observed. In 2019, 2 independent research teams, working separately with newly released position and motion data from the Gaia satellite, made the first confirmed detection of this kind of stretched-out debris trailing behind any open cluster. One team, led by Stefan Meingast and João Alves, and a second, led by Siegfried Rasser, both mapped long, thin streams of former members extending outward from a nearby cluster in 2 opposite directions, trailing along its orbital path through the galaxy. The cluster in question was not this one, however, but its older, more thoroughly unraveled neighbor, the Pleiades. That first detection in the Pleiades caught much of the astronomical community by surprise, since a stream extending hundreds of parsecs beyond the visible cluster had somehow gone completely unnoticed through more than a century of careful, dedicated study of one of the best-known clusters in the sky. The explanation was not any failure of earlier astronomers, but simply a limit of their instruments. The individual stars making up such a stream are faint enough and spread thinly enough across such an enormous area of sky that no observation method before Gaia's satellite-based precision could have gathered enough simultaneous position and motion data to notice the pattern connecting them. Confirming that kind of relationship requires more than a single measurement. Researchers rely on what is called an n-body simulation, a computational technique that calculates the gravitational pull every individual star in a system exerts on every other star, then advances the entire system forward in tiny time steps, repeating the calculation millions or billions of times to model how the whole structure evolves. Modern versions of this technique, run on powerful computing clusters, can simulate the gravitational interactions of many thousands of individual stars simultaneously across simulated spans of hundreds of millions of years, a calculation far too complex to solve with pen, paper, or even simple arithmetic, but well within reach of current computing power. This cluster's own turn came 2 years later. In 2021, Mindgast and colleagues extended the same Gaia-based method across a wider sample of nearby open clusters, this one included, and confirmed that it too trails genuine, measurable streams of former members, stretching outward on the order of 100 parsecs, well over 300 light-years, beyond its visible, familiar core. Subsequent independent studies using slightly different detection methods have since found broadly similar structure, even as the exact length and shape of the tail remains an active area of ongoing refinement. This single line of discoveries transformed the cluster's slow unraveling from a purely theoretical prediction built entirely on computer simulation into a directly observed, ongoing physical process unfolding in real, measurable data collected within the past several years. Since that initial breakthrough, similar extended tidal streams have been identified, trailing behind a growing list of other nearby open clusters as well, suggesting this is not an unusual property specific to one or two particular clusters, but a general, ongoing feature of how open clusters age throughout the galaxy. What Gaia effectively provided was not a new physical process, since tidal stripping and dynamical evaporation had already been well understood in theory for decades, but the first sufficiently precise set of eyes to actually catch the process in the act across an entire population of clusters simultaneously. A useful preview of this cluster's future already exists, much closer than any computer simulation. The Pleiades cluster, forming the recognizable V-shaped face of the constellation Taurus, sits at a distance of about 153 light-years, making it one of the nearest open clusters to Earth, and carries an estimated age of roughly 625 million years, considerably older than this cluster's own 100 million years. Comparing the two side by side offers something rare in astronomy, an actual observable snapshot of what a cluster like this one is likely to become, rather than a purely theoretical prediction. Surveys using Gaia data place the Pleiades' confirmed membership at somewhere in the range of several hundred stars, considerably fewer than the more than 1,000 still associated with this cluster, despite the Pleiades having started, according to most formation models, from an initial population likely comparable in size. That reduction in raw numbers, spread across an age difference of roughly 500 million years, offers a rough, direct measurement of just how much material a cluster like this one can expect to lose to tidal stripping and dynamical evaporation over a comparable stretch of time. The Pleiades looks nothing like a tight, recognizable knot of stars, the way this cluster still does tonight. Its members are spread across a region of sky roughly 5 times wider. Its stellar density is measurably lower, and a noticeable population of former members confirmed through shared motion and chemical composition, despite being scattered well outside the cluster's traditional visual boundary, now drift as individual, unbound stars trailing behind and ahead of the group's main body along its galactic orbit. Whatever process has already partially unraveled the Pleiades over its longer lifetime is the same process currently, slowly, working on this cluster as well, simply earlier in its course. Modern computer simulations attempt to run that process forward directly. Using detailed models of gravitational dynamics, incorporating the cluster's measured mass, its internal stellar density, and the broader gravitational environment of the Milky Way it orbits within, astronomers can simulate this cluster's evolution numerically, star by star, across tens of millions of simulated years at a time. These models consistently predict that the cluster, as a gravitationally bound, recognizable group, will continue losing members steadily over the next several 100 million years, with most simulations converging on a time frame of roughly 250 million years before the group can no longer be meaningfully distinguished from the general population of stars surrounding it. That number carries real uncertainty, since it depends on assumptions about the cluster's exact internal structure and the specific gravitational encounters it happens to experience along its future orbital path, encounters that cannot be predicted with certainty this far in advance. But the general direction of the prediction is considered robust across nearly every version of the simulation attempted. This specific, recognizable pattern of stars, visible in almost exactly this arrangement to every civilization already described earlier in this account, is a temporary configuration, not a fixed one, and will not persist in a form any future observer, however many generations forward, would still recognize as a tight, distinct cluster. What exactly counts as the cluster's effective end is itself a matter of definition rather than a single dramatic moment. Astronomers generally consider a cluster dissolved once its remaining core density drops low enough and its member stars spread thinly enough that shared motion through space becomes the only remaining evidence any stars ever belong together at all, with no meaningful concentration of stars left to call a center. By that definition, this cluster's ending will not resemble a sudden collapse or a single identifiable event, but a slow, statistical fading, the kind of ending better measured in gradually declining density curves on a researcher's computer screen than in any single dramatic night sky. Not every star departs the same way, or for the same reason. The most massive, brightest named stars in this cluster, already discussed for their short main sequence lifespans, will very likely complete their own individual evolution, swelling into red giants and eventually settling into white dwarfs, well before the broader cluster itself fully disperses through tidal and dynamical forces. Their departure from the visible night sky, in other words, will come through internal stellar aging rather than gravitational ejection, fading from brilliant blue-white giants into far dimmer, cooling embers long before gravity finishes pulling the group apart around them. The cluster's much larger population of smaller, dimmer, longer-lived stars faces the opposite situation entirely. These stars, expected to remain stable on the main sequence for tens of billions of years, will vastly outlast the cluster's gravitational cohesion, meaning nearly all of them will eventually be ejected from the group, one by one, while still burning steadily, continuing to shine for billions of years afterward as solitary, unremarkable stars scattered somewhere across the wider galaxy, carrying no visible sign of the tight, mythologized cluster they were born into. This raises a quieter, more personal question. If a cluster like this one eventually disperses completely, its stars scattering individually across the galaxy while their nuclear fires keep burning quietly for billions more years, then somewhere among the ordinary, unremarkable stars visible in any night sky, including stars far too faint or far too ordinary to have ever inspired a myth, there are very likely former members of clusters that broke apart long before recorded human history began. The Sun itself is widely believed by astronomers to have formed within its own birth cluster roughly 4.5 billion years ago, alongside potentially thousands of sibling stars sharing its original composition and formation history. That birth cluster, whatever it originally looked like, dispersed so long ago and has had so much time to scatter across the galaxy's vast rotational structure that identifying any of the Sun's specific stellar siblings today remains extraordinarily difficult, requiring painstaking comparisons of chemical composition and orbital motion among candidate stars scattered across enormous distances. A small number of possible candidates have been proposed by researchers studying this exact question. One of the more widely discussed, a star named HD 162826, sits about 110 light-years from Earth in the constellation Hercules, close enough to be visible through an ordinary backyard telescope on a clear night. Chemical analysis published in 2014 found its detailed composition right down to the precise abundance of individual elements, unusually similar to the Sun's own, matching the kind of signature expected from stars that formed together in the same original birth cluster. Its exact orbital history has also been modeled as broadly consistent with having drifted apart from the Sun's position over roughly the Sun's own lifetime, though, as with every proposed solar sibling, the case remains a strong statistical argument rather than a settled, universally accepted fact. No candidate identified so far has been confirmed with the same certainty used to establish membership in a still intact, currently observable cluster like the one at the center of this account. In a very real sense, the Sun's own birth family is already lost in exactly the way this cluster's family is only beginning to lose its own members now. None of this happens quickly, measured against a single human life. 250 million years, the rough span simulations suggest, before this cluster loses its current identity, is difficult to hold in mind at any meaningful scale. It is longer than the time separating the present moment from the appearance of the very first dinosaurs on Earth, longer than the entire history of complex animal life crawling onto dry land, a span in which entire mountain ranges have risen from flat ground and eroded back down to nothing, in which continents themselves have visibly drifted across the face of the planet. To put a rough number on that drift, tectonic plates on Earth typically move at somewhere between 2 and 10 centimeters per year, comparable to the rate a human fingernail grows. Multiplied out across 250 million years, that slow, almost imperceptible pace is more than enough to have shifted entire continents by thousands of kilometers, opened and widened entire oceans, and assembled and broken apart supercontinents more than once over. The same 250 million years in which this cluster is expected to fully disperse is, on Earth, roughly enough time for the planet's entire surface geography to be rearranged beyond recognition more than once. Against that backdrop, every human civilization described earlier in this account, the Greek poets, the Babylonian astronomers, the Aztec priests, watching for a fire that might or might not be relit, the Māori communities marking each winter's return of these same stars, occupies a span of time so brief relative to the cluster's own remaining lifetime that it barely registers as a fraction of a single tick on this particular clock. And yet, brief as that span has been, it has been long enough for essentially every major human culture, working entirely independently, to look up, notice this same small temporary pattern of light, and decide for reasons of their own that it meant something worth remembering. The pattern currently visible overhead, then, is best understood as a single frame taken from a very long, very slow film. Before this cluster existed in its current recognizable form, its material drifted for billions of years as diffused, formless interstellar gas, scattered thinly enough that no single point of light marked its presence in the sky at all. After it disperses, its former members will continue existing individually, some as white dwarfs, most as ordinary, long-lived stars, scattered quietly among the general stellar population, no longer recognizable as having ever belonged together in the first place. The tight, familiar shape currently visible on a clear winter night, named and renamed across dozens of unconnected human cultures, is neither the beginning nor the end of this material story, only the one relatively brief chapter in which it happened to take a shape organized enough and bright enough for a species capable of storytelling to notice, and to build an entire mythology around a pattern that was never going to last. Mythology was only one of the ways humans engaged with this pattern of light. Long before anyone understood what a star actually was, people also used this same cluster for something far more practical, telling time, finding direction, and eventually, once instruments became available, simply trying to see more of it than the naked eye ever could. Begin with a text older than most surviving buildings. Among the oldest surviving references to this cluster in Western literature is a passage from the Book of Job, part of the Hebrew Bible, generally believed by scholars to have been composed sometime between the 6th and 4th centuries BCE, though drawing on material and poetic traditions considerably older still. In it, God challenges Job with a series of questions meant to illustrate the limits of human power, asking in one well-known line whether Job can bind the chains of this cluster or loosen the belt of the constellation Orion nearby, treating both as fixed, untouchable features of the created universe, entirely beyond human control. The original Hebrew word used in that passage, transliterated as chema, appears again later in the same book, in a separate passage generally translated as asking whether Job can direct the specific bindings of this cluster the way the divine voice speaking to him claims to, again framing the cluster as something fixed and ordered by a power well beyond human reach. It appears once more in the Book of Amos, where a related passage credits God with having made both this cluster and the constellation Orion, again pairing the two directly, exactly as Greek mythology would later pair them through the story of Orion's endless pursuit. A similar pattern appears independently on the African continent. Among Sotho and Zulu communities in southern Africa, this cluster's heliacal rising in early winter has traditionally been known by names typically translated as the digging stars, marking the specific point in the year when the ground was considered ready for planting the season's first crops. Elders in some communities historically held responsibility for tracking the cluster's exact seasonal appearance and formally announcing the start of the agricultural season to the wider community, a role structurally similar to the priestly sky-watching duties already described in ancient Mexico, ancient Babylon, and ancient China, despite no direct historical contact connecting any of these societies. Centuries of translators working from Hebrew into Greek, then Latin, and eventually into English, largely preserved this specific identification, meaning the word rendered as Pleiades in most English translations of the Bible, including the King James Version completed in 1611, refers to this same physical cluster of stars still visible tonight. Not every translation handled the term identically. The Latin Vulgate, translated primarily by the scholar Jerome in the late 4th century, rendered the same Hebrew word as Vergiliae, a Latin name for this cluster tied to its seasonal rising near the start of summer, connecting the biblical reference back to the same Greco-Roman naming tradition already carried through Hesiod's farming calendar centuries earlier. Some later English translations, working from slightly different manuscript traditions or taking a more cautious philological approach, rendered the same word more generically as the 7 stars, rather than committing to the specific identification, though the great majority of major English translations, from the King James Version through most modern editions, have consistently settled on Pleiades as the intended meaning. Travel now across the widest ocean on Earth. Across the islands of the Pacific, from Hawaii to New Zealand to countless smaller archipelagos in between, this cluster served a function even more demanding than calendar keeping, helping navigators cross thousands of kilometers of open ocean without any instrument beyond the sky itself. In Hawaiian tradition, the cluster is known as Makali, and its position at the horizon at sunset was used to mark the beginning of the traditional New Year season called Makahaki, closely paralleling the seasonal role Matariki plays for Māori communities further south. Traditional Pacific wayfinding relied on memorizing the exact point on the horizon where specific stars, including this cluster, rose and set at different times of year, combined with careful attention to ocean swells, wind patterns, and the behavior of seabirds, to hold a course across open water for weeks at a time, with no compass, no chart, and no instrument of any kind. Navigators trained in this tradition organized their knowledge around what is often called a star compass, a mental framework dividing the horizon into distinct houses, each one marked by the specific star or cluster expected to rise or set at that point during a given season. This cluster occupied a fixed, memorized position within that mental compass, allowing a trained navigator, lying in the hull of a moving canoe, watching the sky through a small opening, to continuously check the vessel's heading against the star's expected position, correcting course by feel and memory rather than by any physical instrument. A skilled navigator was typically expected to memorize the rising and setting points of well over 100 individual stars across the full star compass, along with the specific sequence in which they appeared and disappeared across an entire night and across the full turning of the seasons, an oral training regimen that could take a decade or more of dedicated apprenticeship to fully master. This cluster's own entry in that memorized sequence was considered a particularly reliable anchor point, bright and recognizable enough to be identified quickly even under imperfect sky conditions, when a fainter or more solitary star might have been difficult to pick out with confidence. This body of navigational knowledge nearly vanished during the 20th century, as motorized vessels and modern instruments replaced traditional wayfinding across most of the Pacific. In 1976, a Hawaiian voyaging canoe named Hokulea sailed successfully from Hawaii to Tahiti, a distance of over 4,000 kilometers, using only traditional wayfinding techniques taught by a Micronesian navigator named Maupia Lug, deliberately reviving knowledge that had nearly disappeared. One brief, imagined moment, offered purely as illustration, not as a documented account of that specific voyage. Picture, only as illustration, a single night somewhere in the middle of that 4,000-kilometer crossing, no land visible in any direction, ordinary starlight, the only fixed reference point left. A navigator lying near the hull, watching this same cluster clear the horizon at exactly the expected point, adjust the vessel's heading by some small, deliberate fraction, trusting a memorized pattern over any instrument, because there was no instrument to trust instead. This specific scene is not drawn from any published log of the 1976 voyage, and should not be treated as a factual account of it. It exists here only as a brief, speculative illustration of what that kind of star-based navigation would have actually required, moment to moment, far from any shore. That voyage, and the training program it launched, directly reintroduced techniques involving this cluster's seasonal position to a new generation of Pacific navigators, and Hokulea has since completed multiple additional voyages, including a full circumnavigation of the globe, completed in 2017, using essentially the same star-based methods. The broader cultural impact of that first 1976 voyage reached well beyond navigation itself. It arrived during a period of significant cultural revival across Hawaii and the wider Pacific, and its success helped demonstrate, publicly and undeniably, that the ocean crossings responsible for originally settling islands scattered across thousands of kilometers of open Pacific water were the result of sophisticated, deliberate navigational science, not accident or lucky drift, a point some earlier 20th century academic theories had wrongly questioned. This cluster's seasonal position, memorized and applied by a new generation of trained navigators, played a small but real, functioning part in demonstrating exactly that. Now, the seas closer to Europe. European and Mediterranean sailors maintained a parallel, independently developed maritime tradition centered on this same cluster's movements, distinct from the agricultural calendar use already described earlier in this account. Ancient Greek and Roman sailing manuals treated the cluster's pre-dawn rising in spring and its evening setting in autumn as the effective open and close of the safe sailing season across the Mediterranean, since the autumn setting roughly coincided with the onset of the region's more violent seasonal storms. The Roman naturalist Pliny the Elder, writing in his encyclopedic Natural History in the 1st century CE, described this same seasonal rule directly, warning sailors and farmers alike of the specific dates connected to the cluster's rising and setting and the storms that reliably followed. His account, widely copied and referenced throughout the medieval period across Europe, helped carry this same practical, sailing-focused association forward for well over 1,000 years after his own death, long after the original Roman maritime empire that first relied on it had fallen. This convention persisted, in modified form, well into the medieval and early modern periods of European maritime history, referenced in navigational manuals and sailors' almanacs used across the Atlantic trading routes that connected Europe, Africa, and the Americas beginning in the 15th century. A ship's navigator without access to precise mechanical timekeeping, which remained unreliable at sea until the 18th century development of the marine chronometer, faced what became known in Britain as the longitude problem, an inability to determine a ship's precise east-west position without an accurate clock to compare local time against a known reference point. That problem was eventually solved by an English carpenter and self-taught clockmaker named John Harrison, who spent much of his life, beginning in the 1730s, developing a series of increasingly precise marine chronometers capable of keeping accurate time despite a ship's constant rocking, temperature swings, and humidity. Harrison's fourth and most successful design, tested at sea in the 1760s, finally allowed British ships to determine their longitude with genuine confidence, gradually rendering older calendar checks based on stellar risings and settings, including this cluster's own long-used seasonal markers, a secondary backup method rather than a primary navigational necessity. Until that problem was solved, a navigator could still use this cluster's seasonal rising and setting as a rough, reliable calendar check against dead reckoning navigation, a use entirely separate from, though historically overlapping with, its much older role as a farmer's seasonal marker. Now, the moment someone finally looked closer. For thousands of years, across every culture already described, human knowledge of this cluster was limited entirely to what the naked eye could see. 6 stars, sometimes 7, occasionally more for a sharp-eyed observer under excellent conditions. That limit held until 1610, when the Italian astronomer Galileo Galilei turned one of the earliest astronomical telescopes toward the cluster and published his findings in a short book titled Sidereus Nuncius, or the Starry Messenger. The instrument Galileo used was, by any modern standard, remarkably crude. A simple tube fitted with hand-ground glass lenses he had shaped himself, offering a magnification of roughly 20 times, and a field of view so narrow it could only capture a small fraction of the full cluster in a single glance. Despite those limitations, primitive compared to even an inexpensive department store telescope available today, it was more than sufficient to fundamentally rewrite what anyone previously believed about how many stars actually occupied that small patch of winter sky. Where centuries of naked eye observers had counted a handful of stars, Galileo's telescope, primitive by modern standards but powerful enough to change the terms of the conversation permanently, resolved approximately 36 individual points of light in the same small patch of sky. He included a hand-drawn star chart in his published account, carefully marking which stars had been visible before his observation and which had only become visible through the telescope, a direct documented moment in which the cluster's true population was first shown to exceed by a wide margin anything human vision alone had ever suggested. Sidereus Nuncius, published within months of Galileo's first telescopic observations, did far more than simply document extra stars in one small cluster. The same short book also announced his discovery of 4 moons orbiting Jupiter, and revealed that the Milky Way itself, long assumed to be some kind of continuous glow or vapor, was in fact composed of countless individual stars, too faint and too closely packed for the naked eye to resolve. Taken together, these findings challenged the prevailing Aristotelian assumption that the heavens were fixed, finite, and fully accounted for, contributing directly to the broader astronomical upheaval that would eventually put Galileo in conflict with religious authorities later in his life. The specific detail about this cluster, though far less politically explosive than his observations of Jupiter's moons, quietly established the same fundamental principle, that the sky, examined closely enough with a sufficiently capable instrument, always contained more than what any previous generation of unaided observers had assumed was the complete picture. That distinction between what the naked eye can see and what actually exists is precisely the same distinction later confirmed with far greater precision by Hipparchus and Gaia, revealing not 36 stars, but well over 1,000. Galileo's rough telescope in 1610 and a billion-star space satellite 4 centuries later, were, in a direct traceable sense, answering exactly the same question, each simply pushing the boundary of what could be measured a little further than the instrument before it. That boundary has kept moving ever since. In 1771, the French astronomer Charles Messier included this cluster as the 45th entry in his now famous catalog of deep sky objects, a list originally compiled for a fairly mundane practical reason: to help comet hunters, Messier's own primary interest, avoid mistaking a well-known, unmoving cluster or nebula for a genuine moving comet. Messier spent much of his career scanning the night sky specifically in search of comets, a pursuit that had earned him the nickname the Ferret of Comets from King Louis XV of France, and he grew frustrated enough with repeatedly rediscovering the same fixed, non-moving fuzzy objects that he began systematically cataloging them, simply to rule them out more efficiently in future searches. His final catalog, completed with the help of collaborators, eventually listed 110 objects ranging from star clusters like this one to distant galaxies and glowing nebulae, none of which particularly interested Messier himself, who valued each entry mainly for what it was not: a comet worth chasing. The cluster's designation as Messier 45, still in routine use among astronomers and amateur observers today, is a small, functional footnote from an 18th century comet hunting project, entirely disconnected from any myth, calendar, or scripture, yet still attached to the very same handful of points of light that opened this account. Amateur astronomy societies, most tracing their organized origins back no further than the 19th century, adopted this cluster early on as one of the most reliable, rewarding targets for a beginner with a small telescope or a simple pair of binoculars, a status it retains today in observing guides and astronomy club meetups across the English-speaking world. That amateur involvement extends well beyond casual observation. The American Association of Variable Star Observers, a citizen science organization founded in 1911, has spent well over a century coordinating brightness measurements submitted by amateur astronomers around the world, including tracked observations of Pleiades during its recurring shell star episodes described earlier in this account. Those crowdsourced measurements, gathered by hobbyists using modest backyard equipment rather than professional observatories, have contributed real, usable data to the same body of research, confirming exactly when and how dramatically this particular star's brightness shifts over time. The cluster also remains one of the most frequently photographed deep sky objects among modern amateur astrophotographers, largely because of the pale blue reflection nebula surrounding its brightest stars, faint enough to be invisible to the eye through any backyard telescope, but readily captured through a long exposure camera sensor and modest post-processing, a hobby now accessible to anyone with a basic camera, a simple tracking mount, and a reasonably dark sky, requiring a small fraction of the specialized equipment and expertise that would have been necessary even a few decades ago. Not every modern development has made this cluster easier to see, however. The same decades that brought amateur astrophotography within easy reach also brought a steady, measurable increase in artificial light pollution across most of the English-speaking world, gradually erasing this cluster's fainter members from ordinary backyard view, even as professional instruments continued mapping it with ever greater precision. In response, a growing international movement formalized in the United States through the founding of the International Dark Sky Association in 1988, has worked to identify, protect, and expand areas of genuinely dark night sky, certifying specific parks and reserves across the United States, the United Kingdom, and elsewhere as officially protected dark sky locations. That movement has directly restored, for visitors to a certified dark sky park, something close to the same unaided view of this cluster that every culture already described in this account would have taken completely for granted. 6 or more individual points of light, visible without any instrument at all, in a sky increasingly rare and increasingly deliberately preserved. Specific certified dark sky locations now draw visitors specifically for this kind of view, including Cherry Springs State Park in rural Pennsylvania and Northumberland International Dark Sky Park in the north of England, both regularly recommended in modern stargazing guides, precisely because they still offer something close to the same naked-eye sky ancient Babylonian, Greek, and Māori observers would have seen without any special effort at all. From an ancient Babylonian court astronomer squinting at the pre-dawn horizon to a Pacific navigator memorizing a star's exact rising point, to a hobbyist tonight stepping into a backyard with a department store telescope, the basic act being performed, watching this particular small cluster of light and trying to understand it a little better, has remained recognizably the same across roughly 3,000 years of continuous human attention. Every method described in this part of the account, biblical, navigational, agricultural, telescopic, cataloged, and now deliberately preserved against artificial light, approaches this same small cluster from a different angle, yet arrives at a strikingly similar conclusion. It is a fixed point worth returning to, worth tracking, worth protecting, and worth passing down, in one form or another, to whoever happens to be paying attention next. Everything described so far, the myths, the measurements, the navigators, the satellites, all points back to the same small cluster of light, still hanging in the same patch of winter sky it has occupied for the entire span of recorded human history. It will not stay there forever, but it is there tonight. Return one more time to the simplest version of the scale involved. This cluster is about 100 million years old. The universe itself is roughly 13,800,000,000 years old. Measured against the full age of everything that exists, this cluster has been shining for a little less than 1% of that total span, a genuinely young, recent arrival on a stage that was already almost fully assembled long before its first star ignited. And yet, measured against a single human life, 100 million years might as well be forever. There is no need to hold that number carefully. It can simply rest there, unresolved, the way a very large number often does right before sleep. In, out. Every civilization named across this account, Babylonian, Greek, Aztec, Māori, Chinese, is a flicker so brief against that number that it barely registers as a rounding error. And still, each one of them looked up, found this same small pattern, and decided it was worth remembering. That is, in its own way, the entire story. A short-lived species on a small planet orbiting an unremarkable star noticed an even shorter-lived cluster of stars nearby and could not stop itself from finding meaning in the coincidence of timing that let both exist briefly at the same moment. One brief imagined scene offered only as illustration, belonging to no particular century or culture in this account. Picture only as illustration someone standing outside on an ordinary night, long before telescopes, long before satellites, long before any of the specific names or dates already described. No profession is assigned to this person, no country, no century. The scene is left deliberately unplaced because it could belong to nearly any point across the last several thousand years of this account. They notice the same 6 points of light noticed by a Greek shepherd, a Māori family, a Bedouin traveler, an Aztec priest, arranged in almost exactly the same small, tight cluster, low over the horizon. They do not know what a star is. They do not know how far away it sits, or how old it is, or what will eventually happen to it. They simply stand still for a moment, looking up, the way countless unrecorded people across countless unrecorded nights must also have done, and then they go back inside, carrying nothing more than the simple fact of having looked. This particular figure is invented, deliberately unplaced in time or geography, offered only to stand in for the uncountable real observers whose specific names, cultures, and nights were never written down at all. The light arriving right now left those stars a long time ago. 444 years, to be specific. Every photon completing that journey tonight began its trip while global maps were still missing entire continents. Roughly the same years a young playwright in England was first putting pen to paper in a small country theater on plays that would still be read centuries later. The light left before any of that was finished. It has been traveling ever since, indifferent to plays, playwrights, or any of the centuries that followed. It has been traveling uninterrupted through the near total emptiness of interstellar space ever since. Nothing blocked it. Nothing slowed it down. It simply arrived on schedule, exactly as it has every clear night for centuries. Think, briefly, of all 8 names at once without dwelling on any single one. Atlas, Pleiades, Alcyone, Maya, Electra, Taygeta, Cylano, Sterope. A Titan, his wife, and 6 daughters who were never quite 7 and were never quite 6 either. Each one now just a temperature, a mass, a spectral line on a graph somewhere. And still, each one keeps a name older than most languages currently spoken on Earth. That is enough detail. It can rest there now, unfinished the way most things eventually do before sleep. Think for a moment only of Alcyone. 6 times the mass of the Sun. 13,000 degrees at its surface, more than twice as hot as daylight itself. A hidden companion star, orbiting close enough that no telescope has ever fully separated the two. None of that needs to be remembered. It only needs to be pictured briefly, then allowed to fade, the way a bright light fades gently into the dark once eyes have adjusted. Picture briefly only Pleione, spinning close to the edge of what gravity can hold together, shedding a thin ring of light on and off across decades, across centuries, without ever asking permission from anyone watching. Somewhere within that cluster, right now, Pleione is either mid-eruption or resting quietly between episodes. Either way, it continues. Consider, quietly, just the dust. A pale blue haze wrapped loosely around the brightest stars. Not left over from their birth, simply passing through by coincidence at exactly this point in a very long journey. Scattering blue light outward in every direction, the same quiet physics that colors any daytime sky. That haze will drift on, eventually, and the stars will keep shining without it. For now, Tonight, it is still there, softening every point of light it touches. Recall, gently, only a fire that was almost allowed to die. Centuries ago, in a valley far from here, every flame in an entire empire went dark at once. Priests climbed a mountain and waited for this same cluster to reach the top of the sky. It did. It always did. A new fire was lit, carried by torch to every home, and the world, as far as anyone there knew, was allowed to continue. Hold, for a moment, only a rock rising out of the ground. 7 sisters, a bear, claw marks carved deep into stone as it climbed toward the sky. The rock is still there tonight too, in Wyoming, fluted and silent under the same stars the story says it once carried upward. Turn, briefly, only to the smallest star ever found here. Too small to be a star, too warm to be a planet. The first of its kind ever confirmed, found quietly among this cluster's fainter, uncounted members. It does not burn the way its brighter neighbors do. It simply exists, dim and patient, at the very edge of what counts as a star at all. Think, for a moment, only of an older, more scattered cousin. 600 million years from now, give or take, this cluster may look the way the Pleiades looks tonight, spread wide, thinned out, its tightest days long behind it. That is not a warning. It is simply the next stage of the same slow process already quietly underway. Picture, briefly, only the sun's own lost family. Billions of years ago, the sun had brothers and sisters too, born from the same collapsing cloud, scattered since across the galaxy, mostly untraceable now. One candidate, a quiet star in Hercules, may be one of them. Consider, quietly, just how strange it is that such a search is even possible. Comparing the precise chemical fingerprint of one star against another across 100 light-years of empty space to ask whether they might once have shared a birthplace billions of years ago was not a kind of question earlier centuries had any way of even framing, let alone answering. It required understanding what stars are made of, how to read that composition from their light alone, and how to model the slow, complicated drift of orbits across the galaxy over unimaginable stretches of time. That such a question can now be asked and partially answered using nothing but starlight collected from Earth says something quiet but real about how far this particular kind of attention has come since anyone first simply looked up and wondered. No one is entirely certain. Perhaps no one ever will be. In, out. The stars do not know they were named after sisters, or gods, or fires that were almost allowed to die. They do not know a satellite has mapped their positions to within a fraction of a percent. No memory of a Hawaiian navigator lingers in their light, and none of a Babylonian scribe pressing their name into wet clay. A poet in England once compared them to fireflies caught in a silver braid, and they carried on, entirely unaware of the comparison. They simply continue doing what they have always done, burning, slowly cooling, drifting very gradually apart from one another, indifferent to every story built around them. That indifference is not unkind. It is, if anything, a kind of quiet reassurance. The stars were there before any of these stories began. They will still be there after every listener tonight, and everyone they have ever known is gone. Some things do not need an audience to keep existing. They simply exist steadily on their own schedule, whether anyone happens to be watching or not. There is something restful in that thought, if it is allowed to simply sit without being examined too closely. Nothing here is waiting on anyone to solve it, or finish it, or stay awake for it. Somewhere out along that newly discovered stream of former members, a single, faint, unnamed star is drifting quietly away from the group that raised it. It does not know it is leaving. It only knows its own slow path, curved gently by gravity, carrying it very slowly outward, star by star, year by year, the same way it has for longer than anyone has been tracking it. Consider, quietly, just a clockmaker working alone for decades on a single stubborn problem. Ships lost for centuries simply for lack of an accurate clock at sea. He built one anyway, small enough to survive the ocean's constant rocking, precise enough to finally answer the question. After that, the stars became a backup plan instead of a necessity, though this same cluster kept its place in the almanacs regardless. Recall, gently, only ordinary people watching one particular star from their own backyards. Not professionals, not observatories, just careful attention, submitted patiently, year after year, to anyone willing to collect it. A star's flickering brightness, tracked faithfully by hundreds of strangers who simply wanted to help notice something real. In a few 100 million years, it will simply be an ordinary star among billions of ordinary stars, with no visible sign it ever belonged to anything as bright or as named or as mythologized as this cluster. That is not a sad ending. It is simply the next chapter, unfolding at a pace too slow for any single lifetime to notice. Hold, for a moment, only a court astronomer in ancient China, recording a single mansion of sky. Mao, 28 mansions in total, and this one small enough to fit inside a single glance upward. 2,000 years of records kept faithfully of something that never once asked to be recorded. Hold, for a moment, only the specific shape of that record. Bamboo strips, then silk, then paper, carrying the same handful of characters forward across dynasties, empires rising and falling around a small, stubborn tradition of simply writing down where one particular patch of sky happened to be on one particular night. No single scribe across those 2,000 years could have known how long the habit would continue after them, or that anyone tonight, in an entirely different language, on the opposite side of the planet, would ever hear about it at all. Turn briefly only to the desert and the word Al-Thuraya. Rain somewhere close once this pattern reached a certain point in the sky. A whole season's herding decided by 6 small points of light, trusted completely for centuries, without ever once explaining why they could be trusted at all. Think, for a moment, only of 7 sisters guarding fire on the end of a stick. A crow, a trick, a single stolen ember, and suddenly the whole world had warmth. The sisters kept their place in the sky anyway, embers and all, exactly where the story left them. Picture, briefly, only 9 stars instead of 7. Food from the ground, food from the air, fresh water. Salt water, wind, rain. Those who are gone, those who are still hoped for. A single winter rising, asked to carry all of that at once, every year, for longer than anyone can trace. Consider, quietly, just an old question asked in an old book. Can this cluster's chains be bound? Can its ordering be loosened by anyone at all? The answer in the text was simply no. The stars were never meant to be controlled, only noticed. None of it needs to be sorted out fully tonight. It can simply sit, unresolved, the way old questions often do, right before sleep. Tonight, someone was watching. That is enough. It was enough for a Greek shepherd watching the horizon for the safe start of sailing season. It was enough for a Māori family, marking the return of Matariki with quiet remembrance of those lost the year before. A Bedouin traveler once read the coming rains in the timing of a single rising star, and that too was enough. Galileo needed only a handmade telescope, one quiet evening, and more stars appeared than he had ever expected to count. It is enough now for whoever is still listening, eyes closed, letting this same old pattern of light carry them gently towards sleep. Recall, gently, only a canoe crossing open water. No compass, no chart, only memory and the sky, and this same cluster rising in exactly the place it was expected to rise. 4,000 kilometers, Hawaii to Tahiti, guided in part by a pattern of light no different from the one visible tonight. Hold, for a moment, only a handmade telescope, pointed upward for the very first time. 6 stars became 3 dozen, almost instantly, the moment someone thought to look a little closer. A single evening, a single instrument, and the sky was suddenly larger than anyone had known to expect. Turn briefly, only to a comet hunter, mildly annoyed by a cluster that refused to move. He wrote it down anyway, if only to stop mistaking it for something it was not. 2.5 centuries later, that same small practical annotation is still exactly how astronomers refer to it today. Think for a moment only of a dark field, far from any city, where this same pattern is still easy to find. 6 points of light, unaided, the same 6 a Babylonian scribe once watched rise before dawn. Some places have worked, quite deliberately, to keep that view intact. Nothing further is required. The cluster will keep drifting. The individual stars will keep aging, each on its own timeline, some toward a quiet white dwarf ending, others toward a more dramatic one. The tidal tail will keep stretching, slowly, invisibly, across hundreds of light years. None of it requires anything further from anyone listening right now. It was already in motion long before tonight began, and it will remain in motion long after this particular story ends. There is nothing left to track, nothing left to calculate, nothing left to remember before sleep. Only the simple fact of the light still arriving exactly on schedule. Consider, quietly, just how many other eyes have rested on this exact pattern. Not a precise count, since no one kept one, but across roughly 3,000 years of written record alone, and countless thousands of unwritten years before that, the number of individual human eyes that have paused, however briefly, on this same small cluster is almost certainly large enough to be meaningless as an exact figure, and meaningful only as a rough general sense of scale. Every one of those moments of attention has ended the same way. The observer eventually looked away, or closed their eyes, or fell asleep, while the stars themselves simply continued on, entirely unaffected by whether anyone was still watching. Recall, gently, only that this is not the only cluster of its kind. Countless other loose, temporary groupings of young stars exist, scattered throughout this galaxy alone, most with no name, no mythology, no satellite dedicated to mapping their every member. This particular cluster is not special in any deep physical sense. It is simply close enough, bright enough, and old enough in human memory to have accumulated an unusually rich collection of names and stories along the way. Somewhere else in the galaxy, right now, an equally young, equally temporary cluster is quietly forming, entirely unnoticed, with no one yet watching it at all. 444 years old, and still, tonight, right on time. The pattern is still there. It always was. It will still be there tomorrow night, whether or not anyone happens to look up and notice. That, more than anything else described tonight, is the part worth carrying quietly into sleep. Not the exact number of stars, not the name of any single one of them, just the simple, steady fact that some things continue, patiently, without needing anyone's attention to keep doing so. One story, 6 stars, or 7, or 1,000, depending on how closely anyone bothers to look. One fire almost allowed to die and relit anyway. One rock rising slowly out of the ground, carrying 7 sisters upward. One satellite mapping 1 billion points of light with more patience than any human observer ever could. One cluster quietly coming apart, star by star, at a pace far too slow for tonight to notice. None of it needs to be finished before sleep arrives. It was never going to finish tonight anyway. It has been unfolding for 100 million years, and it will keep unfolding long after this recording ends, long after tonight becomes simply another quiet night, folded into all the others. There is nothing left to hold on to. Only the pattern, steady, overhead, exactly where it has always been. Quiet Science at Bedtime will be back with another true story from the night sky, for anyone who wants to drift off to something real again. Everything you heard tonight is real. The Pleiades is out there right now. Sleep well.